everyone, my name is Athar Yadav and today we are going to talk about some important topics of quantum computing, which are quantum gates such as pauli X gate, pauli Y gate, pauli Z gate, toffoli gate, which is also known as cnot gate. We are going to also talk about cnot gate, fredkin gate, and the most important one, Hadamard gate. And also we are going to talk about De Morgan's law. So here we start. So our first topic is what are quantum gates. Quantum gates are building block of a quantum circuit. Just like the classical gates, which are the building block of a classical circuit. But there is one huge difference, which is quantum circuits or the quantum gates work on qubits, which are 0 gate and 1 gate. And they are reversible. They can be represented reversible because of their property of superposition. Now we are going to talk about the quantum gates. The first gate is Hadamard gate. Do you know it is one of the most important quantum gates we are going to use. It is represented by H. And why is it important? Let me tell you. It is important because it is one of the gates which is responsible for superposition of 0 and 1 ket vector. What happens in it is when we input 0 ket here, it gives us a addition of 0 and 1 with some phase difference. And exactly when we put 1 ket here, it gives us another mixture with another phase. So what happens here is Hadamard gate is always used for superposition. We can know multiple possibilities through it. And one of the most important role of it is that it makes certain things into uncertain things, which is the most important law of quantum parallelism. Now, secondly, we are going to talk about pauli gates, which combines X, Y and Z. The pauli gates in quantum are representative of rotation of these qubits. They give you block sphere rotations and axis rotations and phase of the sphere. Now we are going to talk about each of them. First comes pauli X gate, which is represented by normal X, and this gate is just similar to classical NOT gate. What happens here is when we put 1 gate over here, it flips it and changes it into 0, and when we put 0 gate here, it flips it and put it as 1 gate. This is pauli X gate. Now we are going to talk about pauli Y gate. What does pauli Y gate do? It's really similar to pauli X gate, but what it does is it adds phase difference to it, and it also provides rotation to its vector in y-axis. Now we are going to talk about pauli Z gate. It is represented by a simple Z, and what happens here is it does not flip the gate vector. What it does is it provides it a phase difference, and it is really important for interference. And there is one more necessary of pauli gate of Z. What it does is that it amplifies the correct answers in quantum computers, which significantly amplifies the more correct answers rather than the incorrect answers. This was all about pauli gates X, Y and Z. Now let me tell you, where are they really used in our real life? They are used in error correction codes in quantum circuits. They are also used in quantum encryption. Just like classical encryption, there is also a quantum encryption. Now, the third use of these gates are stabilizer circuits. They are also used in stabilizing circuits. These are the uses of pauli gates. Now we are going to talk about 2-qubit input gates. The first one is cnot gate, which is also called controlled NOT gate. What happens here is it takes 2 inputs. One is control bit, another is target bit. When the control bit is 0, then the target bit is not flipped. But if the control bit is 1, then the target bit is flipped. Now we can make the truth table for it. Like this is our control bit and this is our target bit. What would be the output for it? If we take 1 0 here, the control bit is 1, so the target bit would be flipped. The answer would be 1 1. Now what happens is, if the control bit is 0, then the target bit would not be flipped. It would be just 0 and 1. Hence, if we put 1 1, the output will come 1 0. Why is cnot gate such an important gate in quantum? It is such an important gate in quantum because it creates entanglement. Now you will ask me, what is entanglement? Let me tell you what is entanglement. It is a property in which both the inputs are deeply connected with each other, which makes it, if we affect any of the input in them, it can change both of them. This is what entanglement property is, and that's why cnot gate is really an important gate in quantum physics. Now, where are they used? They are used in quantum teleportation, they are used in quantum communication, and they are also used in building multi-qubit circuits in quantum. This is really an important gate in quantum physics, and if we wouldn't have this, it may happen that we would have lost a really important gate in quantum physics. Now we are going to talk about a 3-input quantum gate, which is called cnot gate, which is also called toffoli gate or controlled not gate. The visual representation of cnot gate is this, and let me tell you what happens here. There are 2 control bits, as you can see, and there is 1 target bit. What happens is, whenever the input in both of the control bit is 1 key, then the target bit is flipped, or else if none of them or either of them is a 0 kit, then the target bit is not flipped. This is the speciality of this gate. Let me give you some examples for it. For example, we are going to make a truth table for it. X, Y and Z. This is our control bit. This is control bit, target bit. What would be the output? Y dash and Z dash. Now, if either of them is 0, then the control bit would not be flipped. The answer would be the C, like this. Or both of the control bit is 0, then the target bit wouldn't be flipped. If the control bit, both of them are 1 kit, then the target bit would be flipped, which will be like this. The importance of this gate is, it is universal gate. It can be changed into any gate. And the second advantage of this is, it is a reversible gate, which many of the gates are not. Where is the toffoli gate used? Let me tell you. Reversible computing. It is used in reversible computing, quantum error correction. This is the use of toffoli gate. It is really a very important gate in quantum physics. Now we are going to talk about our last gate, which is Fredkin gate, which is also called controlled swap gate. I will tell you later on why it is called controlled swap gate. First of all, let me tell you a brief introduction about Fredkin gate. It has the ability, to exchange information conditionally without destroying them. That's why this gate is one of the important gates in quantum physics. Now, what happens in this gate? There is 1 control bit and 2 target bits. Ordinary gates had 2 control bit, 1 target bit, right? But here we have 1 control bit and 2 target bits. And what happens is, if we put 0 kit and control bit, then the target bit wouldn't flip. It wouldn't swap. But if we put 1 kit here, then what will happen? The target bits will swap between each other, and the output would be another. Let me show you, give you an example for this. We have X, Y and Z, and outputs are X dash y dash and z dash. What happens is, if we have 0 input and here is 1 0, this two target bits wouldn't be flipped because of having 0 there. It would be 0 1 0. But if we have control bit 1, the input in this will be swapped in the output. It will be like this. Can you see the swap here? This is what fredkin gate is, and its name defines it, controlled swap gate. Now, where are they used? They are used in reversible quantumation. They are also used in quantum routine and switching. They are also used in simulating physical system. This is the importance and the uses of fredkin gate, and our last topic of the gates. Now, talking about the last topic of our session is De Morgan's law. It states, by the way, yeah, we know quantum gates are reversible and they have their own qubit structure, but whereas De Morgan's law significantly helps in quantum physics, and now we are going to know how. The first one, law states there are two laws in it. Not A and B is not A or not B, and not A or B is not A and not B. This is what De Morgan law states. And how De Morgan law is used? Let me tell you how it is used. It reduces quantum gates. As we know, they are really expensive to use. Secondly, sometimes quantum gates has also classical control units. That's where De Morgan law works. Now, here is the conclusion. We talked about quantum gates. They are really necessary. There are many quantum gates, Hadamard gates, which is used for superposition, then toffoli, cnot, pauli gates. They are used for control units and phase difference and revolving of vectors. And then at the last, there comes De Morgan's law, which is also significantly important in quantum gates because of its control units and control structure. Here I end my session. Thank you.